let's be real for a second. For decades, we kind of thought we had the cosmos somewhat figured out, right? Well, scratch that. Recently, some brand new astronomical data has dropped, and it's seriously threatening the standard model of cosmology. It's forcing us to ask a pretty terrifying, but honestly thrilling question. Is our fundamental understanding of the universe just fundamentally broken?
Welcome to today's Explainer. We are diving headfirst into a true cosmic collision today. We're talking observational astronomy crashing right into theoretical physics. Because as you'll see, deep space observations are suddenly threatening to literally rewrite the rules of our most complex mathematical theories. It's a massive detective story, so let's get into it.
Here's our quick roadmap for today's journey. First, we'll look at the dark energy puzzle, followed by hints of evolving energy. Then, we enter string theory, check out the Swampland conjectures, explore a dynamical universe, and wrap up with testing the theories.
All right, starting with part 1, the dark energy puzzle. So dark energy, it's that deeply mysterious force driving the accelerated expansion of our universe. Now, in our standard model, ΛCDM, it's treated as just a constant, unchanging vacuum energy. And it's huge. It accounts for the vast majority of our universe's energy density, just steadily pushing galaxies apart. Astronomers have actually been measuring this steady push for years, mostly by observing distant supernovae and tracking baryon acoustic oscillations. Those are basically massive ripples in the density of matter left over from the very early universe.
But wow, here is where a massive headache begins for physicists. If dark energy is truly just the constant energy of empty space, quantum field theory attempts to calculate exactly how much of it there should be, and it fails spectacularly. It predicts a vacuum energy that is 10 to the power of 123 times larger than what we actually observe. To put that into perspective, it's almost comical how incredibly large that error is. This massive mathematical discrepancy is what we call the cosmological constant problem. Basically, it's a giant red flag telling us that our current standard model is deeply flawed right out of the gate.
Okay, moving to part 2, hints of evolving energy.
Get this, recent data from the DESI survey, which spent years mapping literally millions of galaxies to trace the expansion history of the cosmos. Well, when you combine that with Pantheon plus supernova data, it's showing something completely unexpected. We are actually seeing statistical signals at the 3 to 4 sigma level suggesting that dark energy varies. Now, if you know the world of physics, a 3 to 4 sigma result is a very, very strong hint. It basically means dark energy might not be a static constant after all.
In fact, when researchers map out this new data, the best fit model shows something truly bizarre. They show dark energy hitting a maximum density around a redshift of 0.5, which is roughly 5 billion years ago, and then rapidly decreasing before and after that point. This implies dark energy is a dynamic, evolving force. Think about that for a second. If this holds up, it changes absolutely everything about how we predict the ultimate fate of our universe. Instead of just expanding infinitely into a cold, dark void, what we call the Big Freeze, an evolving dark energy could mean the universe eventually tears itself apart in a big rip, or who knows, maybe even collapses back in on itself in a big crunch.
Which brings us to part 3, enter string theory.
Let's bring in our theoretical profiler here. String theory views the universe not as a collection of zero-dimensional dots or point particles, but as tiny, one-dimensional vibrating threads of energy. The idea is that the specific vibrations of these microscopic strings dictate every single particle and force we see in nature. It theoretically offers a single, unified framework for all physics, the whole shebang. We're talking gravity, quantum mechanics, and yes, potentially dark energy.
Now, string theory has evolved dramatically since the Veneziano model was first proposed way back in 1968. By the 1990s, the math had advanced enough to successfully decode incredibly complex phenomena like black hole thermodynamics. But for us, our focus today is on a massive paradigm-shifting realization that hit the theoretical community in 2018. It's a realization specifically regarding dark energy and a wild mathematical concept known as the Swampland.
All right, part 4, the Swampland conjectures.
This 2018 headline from Quantum magazine absolutely hits the nail on the head. Based on some intense new mathematical conjectures, theorists realized an incredible irony. Listen to this. If dark energy is truly a static, unchanging constant, which is exactly what our standard model of cosmology says it is, then string theory predicts our universe literally shouldn't exist. No way. Instead of fitting into a viable landscape of possible universes, a constant dark energy dumps our universe into what theorists call the swampland. It's basically a mathematical dumping ground for impossible, broken realities. So, the Swampland distance conjectures place these incredibly strict geometric limits on what kind of universes are actually allowed to exist.
The boundaries represent infinite distance trajectories in what's called moduli space, which is essentially just the mathematical parameter space of string theory. If a cosmological model, like one relying on a constant vacuum energy, forces our universe's parameters outside this viable geometric space, well, it falls straight into the swampland. It essentially means the math of string theory is actively rejecting the standard cosmological model of dark energy.
Which leads us nicely to Part 5, a dynamical universe.
So, we have a clear divide here. On one side, there's ΛCDM, the constant vacuum energy that creates a massive mathematical mismatch and lands squarely in the string theory swampland. But on the other side, we have dynamical models, like thawing quintessence or modified gravity. In these models, dark energy actually evolves over time through a rolling scalar field. And here's the kicker. These evolving models perfectly mirror the shifting density that we're now seeing hinted at by that latest DESI data.
For theoretical physicists, this convergence is just a massive sigh of relief. Recent analysis shows that an exotic subset of string models, specifically where the tension of strings is generated dynamically, actually provides an escape route out of the swampland. This dynamical tension string theory perfectly accommodates an evolving dark energy. So you know that shifting, changing dark energy that astronomers are just starting to spot in the sky? It might be the exact mathematical key needed to rescue our universe from the string theory swampland. It's like the cosmic puzzle pieces are finally fitting together.
Let's bring it home with Part 6, testing the theories. The good news is we aren't just relying on theoretical math anymore. To confirm if dark energy is truly dynamical, we're going to rely on upcoming high-precision datasets. We're talking about the European Space Agency's Euclid Space Telescope, the Vera C. Rubin Observatory, and NASA's Nancy Grace Roman Space Telescope, which is set to launch in 2026. By mapping literally billions of galaxies and supernova, these incredibly powerful tools will measure cosmic expansion with unprecedented clarity. They are going to definitively test this changing energy idea and rule out whether the current data is just some systematic mirage.
So, as we look through these incredible new lenses at the cosmos, and as we potentially confirm that the very fabric of our universe is shifting and evolving, you really have to wonder, will our fundamental theories of reality survive the test, or are we standing right on the edge of entirely new physics? Let that sink in for a bit. Keep questioning everything, and I'll catch you in the next explainer.